Wake a little bit. As Luis explained a little bit more about water mist, I will also skip this part or keep it very, very short because it's also a little bit related to water mist, but basically to firefighting system in tunnels. And I can tell you that's good to be here because Britain is one of the leading countries in Europe with firefighting system in tunnels. Come to that later. A little bit about the principles, about some fire testing. As you heard already, water mist manufacturers always want to do full-scale tests. By the way, I'm coming from EFAB. It's a subsidiary of FOGTEC. Now we are, let's say, changed the organization structure a little bit, and I do fire testing. I think almost about 10 years. Many full-scale fire tests for various applications. Then it comes a little bit new parts, compensation with water mist, everything related to tunnel, what is compensations, what we can do. And a little bit a case study, we keep it very short due to time, about the new time crossing, which is not so far away from here. First of all, fire development in tunnels. The problem is, when we look back 10 years ago or 15 years ago, we learned a lot about fire development in tunnels. They can develop much faster than expected in the past. If you still look to guidelines, which are still valid and still the design base in some cases, then it says about 20 megawatt, everything is fine. 30 megawatt, everything is fine. The systems are designed for that, and then you have many minutes, 20 minutes when the fire brigade will arrive, everything is fine. Yeah, we know today that's in many cases not the truth, unfortunately. Next problem are the people. The people do not react as they intended to do. So there were a lot of research works for big emergency doors and but what the people want to do is to do sightseeing. They don't want to. The first thing when they see a fire in a tunnel or even a fire outside, the first thing is they put out their iPhone and make a nice video and put it onto YouTube. That's the most important thing ever. The problem is that people should get out as fast as possible, but they don't. The rescue services cannot be considered as a support for people inside the tunnel. Of course, fire brigade will hate me for this sentence, but unfortunately, that's the truth. Yeah? The fire brigades, there are very few cases where it's a different story, where the fire brigade is exactly at the portal or inside the tunnel, like in the Mont Blanc tunnel. But usually, the fire brigades, they have to approach to the tunnel 5 minutes when they are fast. If there's a traffic jam, they're much slower, and it's not their fault. That's their life. And then they have to go inside the tunnel, and there is also a traffic jam, and people coming out, and they don't know the situation there. So normally you can expect the fire brigade is not earlier than 20 minutes after fire started at the place of the incident. We know, of course, from many incidents that smoke is the danger. Smoke causes the majority of the fatalities in the tunnel or for tunnel fires. And this is also a problem because the time for firefighters to approach to the fire is significantly increased due to the reduced visibility. If you have no visibility, it's just you just remember on a car on a highway driving through fog. No way, you cannot drive that fast with a clear visibility. And I can tell you from Germany, we have no speed limit on the highways. It can be much faster than. And which is also a side story, but it's also important to know that most larger tunnel fires are ventilation controlled. So if you increase the ventilation because you want to get the smoke out, for example, very simple measure, then you increase the fire, which is maybe not a good thing. So we have two major enemies inside tunnels. The one enemy are the trucks, heavy good vehicles. We don't know what is loaded on the trucks, and if they start to burn, and they start to burn quite often, by the way, for technical reasons, for example, then we have in most cases a fire between 30 and 100 megawatt, and even in worst cases it can go up to 200, 250 megawatt. Of course, then we are fully in the ventilation controlled fire. And the time is the issue. If we have the right ignition source, even with a standard truck, then a fire can develop extremely fast. Within 5 to 10 minutes, we have a fully developed fire, or fully developed 50, 80, 90 megawatt fire. And I experienced myself several times as a fire brigade. You arrive 6-8 minutes on the highway with, let's say, a bus or a truck, and the truck is on full fire. And of course, this also can happen inside tunnels. That's why in the past, or at least it's now starting to be introduced into the guidelines like NFPA. Also, the Europeans are slow, but they're intending to change that. The design fire rates or the heat release rates in the guidelines are changed from, as I said in the past, it was just strictly 30 megawatt. And now we are going up to 100, even 200 megawatt in some special cases. But that's the real life and that's the truth. So and of course then we have a problem because our tunnels are in most cases designed for 30 megawatt. Sounds so good, yeah, but now we know we need to design our tunnels for bigger fires. And then, I think it was 15 years ago, or even longer time ago, but 15 years ago in Europe, when we had these big tunnel fires, research started for fixed firefighting system in tunnels. Now we have this triple FS, it's now a fixed wording already. What are the aims of these systems? First of all, it's fire suppression or firefighting. And I know I had long discussions, for example, also with Ricky, what about the wording, what is fire suppression? Because you will see later some curves where you normally would say, okay, fire suppression is for me, it's a clear reduction of the heat release rate. That's fire suppression or firefighting. But you will see it's not the case, or not in all the cases you will reduce the heat release rate. But you change other parameters which will allow a good, let's say, a better situation inside the tunnel. You have to protect the fire spread. So if one car, one truck is on fire, okay, it's a big problem, but it's not a severe problem. The major problem in the past was that the fire spread from the one truck to the next truck. And I think in Mont Blanc it was distances over almost 100 meters. So 100 meter air in between, and the fire spread was across this distance. Of course, we want to get the rescue services in, fire brigade. As soon as the fire brigade is very close to the fire, so where they can work normally, it's no problem. I can tell you from my own experience, from many fire tests, the fire is out within minutes. But the problem is to get them close to the fire. Of course, we want to increase the life safety for tunnel users. These are not really tunnel users, they are watching a demo, but sometimes they're also tunnel users. This is also an aim for of the systems, to buy time to get the people out of the tunnel and to get the rescue services in. Of course, there are more aims of firefighting systems, like improving the performance of ventilation systems. That's quite new. I'll come to that later in more detail. Protection of the tunnel structure, also discussed very critically. Or the compensation of other safety measures within an integrated approach. When you have a holistic design, safety design, then you can do this in a building. It's the normal way to do this because you cannot always apply strict standards. The effect of water mist and tunnel fires. You learned already a little bit about water mist, so I will not go into detail. We have small droplets. Of course, the design of a water mist system is completely different for a building, is completely different of a water mist system inside tunnels. For example, for electronic switchgear cabinets or even office areas, you use water mist systems which are usually having a droplet size much below 100 microns. For tunnels, no way, no chance at all. You need big droplets because you have to get the droplets into the fire. Compared to a deluge system, they are still much smaller and provide a much better cooling potential. Of course, the aim is to convert these droplets into steam. But the good thing is, this will only happen right around the fire. As soon as you wait 1, 2, 5 meters from the fire, there is no steam anymore. But what is the aim is really an enormous and rapid cooling effect. We need this large cooling effect because heat is one of the biggest issues during a tunnel fire. What is also a big thing for why water mist gives a good results is the reduction of radiant heat compared to a sprinkler or deluge system. Used the correct wording. The reduction potential is much higher, so you can even stand really close to a really big fire, 50 megawatts, and you're standing 5 meters, 3 meters away, and it's no problem. Or you feel it on your skin, but if you would have no water mist on, impossible at all. Of course, what is always said about water mist, it's the so-called oxygen depletion effect, so you're vaporizing, you're creating a larger volume around the fire, so you reduce slightly the concentration of the oxygen. Of course, this is also a limited effect for tunnel fires because we always have a forced ventilation in tunnel fires. It's a limited effect, and it just can be used just for pool fires. For solid combustible Class A fires, it has no effect at all. That was the graph for the cooling effect. Just to give you a short overview about different technologies for tunnels, of course we have so-called deluge system, conventional systems. They're used in Japan and Australia since many years. They are strictly based on a flow per area design. It's used between 6 and 12 liters per square meter. I can tell you now from tests, they are not published yet, but I can tell you 6 meters is not enough. When it comes to 10, 12 meters, then you are in an area where also these systems are quite effective. But the problem is, at the moment, as I said, it's not yet published, but at the moment there are almost no fire tests above 30 megawatts, so they were not tested at all. But they're used since many years. Then there are some foam systems used. There were some tests. There's one tunnel in Germany which is equipped with a foam system. I was present there at the activation, so when they do a test, and it's really like a foam party. I will not comment too much on that because I don't think that's a good idea to make a foam party in a tunnel, but it is like that. And then you have a water mist. At the moment, when you, let's say, collect tests from all the manufacturers, of course there are more than one manufacturer from all the manufacturers, then you have much more than 100 full-scale fire tests and even up to 200 megawatts. 200 megawatts fully developed fire when the water mist system was activated. And they're used in France, A86 for example, they're used in the UK, New Town Crossing. The next tunnel is just about to be installed. It's the Dartford tunnel close to London, in Spain, Italy, Russia. And just as a rule of thumb, you can say, okay, they just use around 20 to 30% of the water as a standard or as a deluge system. Now coming a little bit to the nice pictures and some big fires. Just recently, or we are just still during the last working month of a large research project. It's called Solid 2. There was one previous project just called Solid 4 or 5 years ago. And the aim of Solid 2 was not to prove that firefighting systems in tunnels are working. We know that they are working, so there's no proof necessary anymore. But the future comes with the compensation. So we want to compensate safety measures by fixed firefighting systems, or partly compensate safety measures by fixed firefighting systems. And we want to integrate these systems into a holistic tunnel safety system. There are just some figures about the research program we had this year. During spring and summer, we had a large scale fire test program in Spain. There's a nice, in the north of Spain, there's a nice test tunnel where you can do huge fires, and there we had a big test program and also a small workshop where we had the possibility to show a little bit full-scale fire tests. There are some partners, we just will skip this because of time. The major work program is, of course, we have a state-of-the-art analysis. You need to do this. That's this research work, as you all know. And then we want to identify the potential of compensation. Where are the needs? We will come to that. I can tell you, it's ventilation. To upgrade a ventilation system from 30 megawatts to 100 megawatts, it's really a nightmare. It's not because of the design, it's because of costs, room, and especially when you have to upgrade existing tunnels. There was a big part simulation, because at the moment it's still full-scale fire testing, and you heard this also this morning from FM Global, that this is really a costly exercise, and so also in the future we want to reduce these costs a little bit and try to simulate at least partly the results of or the effects of firefighting systems. Of course, some effects of the fixed firefighting systems are as well studied, and what is also very important, the economic evaluation between different types of systems. Not only between different types of firefighting systems, but also between different parts of the tunnel safety system. So if you want to compensate a part of the ventilation with another system, you have to know the costs, and not only just the installation costs, but also the life cycle costs for both systems, and then you can compare this. This is this nice test site north of Spain. This year we had really a bad summer there. It was just not above 20 degrees, unfortunately for my colleagues. It's really a huge test site, 600-meter long tunnel, just to play around, to make fires, to make exercises. The cross-section is like a normal tunnel. It has some drawbacks because of the fire protection itself, so we had to do a lot of measures to protect this tunnel itself, to do fire testing, but in the end it worked out. And we did some truck fire testing with longitudinal and semi-transversal ventilation. So we had a suspended ceiling with some smoke dampers and a smoke extraction system in there. We did also some pool fires, 30, 50 to 60 megawatt and 100 megawatt pool fires, and I can tell you that's really a challenge to do pool fires with this size. And of course, one of the major aims of this research or test program was to study the influence of a firefighting system together with the ventilation. So what is happening there? What are the effects on the ventilation, but also on the firefighting system? We also had some fire brigades there. We had a local fire brigade to do the bad work, to extinguish always after the fire tests. Now they are well practiced in tunnel firefighting, I can tell you. And unfortunately, it's a mining fire brigade, so you will never use them on the roads. But also the Hamburg Fire Brigade and Fire Brigade from the River Elbe Tunnel in Hamburg, they were there also to evaluate their work. So they were just walking around during the fire test and checking how close they can get to the fire. They were also with the breathing apparatus really walking around the fire load itself. On this picture you can see, I would say that's around 20 megawatts truck fire, just with some wood pallets, and that's right after 5 minutes using a very small ignition source. Ignition source was around a pan like this, I don't know, even a quarter of a square meter, and some gasoline, and that's all. And then wait 5 minutes, and then you have this picture. It looks quite nice and impressive when you're standing there. Coming a little bit to curves and to the interesting things now. As I said, we did Class B fires. I just picked now one fire test, and just want to go with you a little bit into the curves. There will be much more publications in the near future. At the moment we're still working a lot with the data and had not really the time to work on the publications, but they will come in the near future. We have, as I said, Class B fires up to 100 megawatts, diesel fires, and they were not covered. That's also quite important to know, because there's written they were extinguished. That's right, they were extinguished, because you check this always when the fire is out, then you go in, again a little bit of gasoline, and then you start to reignite the pool, and then you see if the fire was just extinguished because it was running out of fuel or because it was extinguished by the system. But that's not the normal case, because most of the tunnel fires are hidden fires, and no system ever, no foam system, no deluge system, and also no water mist system really can extinguish these fires. Come to that, why this is so important, we'll come to that later. When you look at the curves, at the top graph is showing the heat release rate, and then you can say, okay, you started the water mist system with 20 megawatt, and then strange. And then the heat release rate was increased to 60 megawatt. You have to know a little bit more details about the measurement system, how you measure the heat release rate in such fire tests. You cannot just, it's not that easy. You measure it by calculating it from the oxygen consumption of the fire. So you have to measure the oxygen concentrations and of course the air velocity and the humidity and the temperatures at a certain point. Problem is that sensors cannot really live with high temperatures, so you have to go really downstream, because if you would measure it directly at the fire, you have 1000 degrees. That's really a challenge for any sensor, so you cannot use this. So you have to at least move around 60, 90 meters away from the fire on the downstream side. And then you measure the oxygen, but then just calculate, okay, let's assume an airspeed of 3 meters per second, which is quite usual for a fire test. Just the time which the air needs to travel from the point of the fire to the sensor is around 90 seconds. That's quite a lot. And then you have still needs the time to suck the air from the tunnel to your sensor itself. So normally you have around 1 to 2 minutes, at least 1 to 2 minutes delay, just because of the measurements. This, of course, has to be taken into account. Furthermore, you have to know this method is quite sensitive to any changes in the system. So if you activate a fire suppression system, then forget your measurements. Heat release measurements, they are not right anymore. Or they are not right at this period of time, let's say 30 seconds, 1 minute around this action, they are measuring just bullshit, because you're mixing up everything, you're changing the airspeed and everything, so that's not right. So the important area, let's say, starts around here. There we have the system activated. We still have 60 megawatts, because we are, or in this case, we are not using this fire switch off, but you have a suppression system, and this system takes time to fight with the fire. And then you see that the heat release rate is going down with the pool fire, and then it was off. This, what you see here, the heat release rates are this so-called reignition of the pool. So pool by pool, we then went through with gasoline and reignited. It's hardly to see, but you will get this presentation later on, so then you can have a closer look. You see around the fire, within seconds, you have around 1000 degrees, 800 to 1000 degrees. If you would wait a bit longer, then you have this so-called Rix-Water start curve, even showing 1300 degrees without any problem with such a fire. And here you see also some temperatures measured a bit downstream, and you see this immediate reaction on the water mist. You have an immediate cooling effect. So even you have a fire burning there, because the fire is not out yet. Fire is still burning with a significant 50 megawatt, 40 megawatt. You can go to the fire. You can approach the fire, because the temperatures around the fire, it's cold enough to go there. It's quite a different picture, same picture, not different picture when you look at Class A fires, and that's of course now one of the things which always leads to strong discussions about these systems. Usually your fire load is covered, it's fully covered. Look at your trucks on the roads, they are covered. Almost in no cases the fire load is open, that's one thing. Or maybe just the outer areas is open, but you cannot really introduce your firefighting agent into the fire. That's just absolutely impossible, just from physics. You can do this with the firefighting tools, because you use much more water and you can really point your water where it's needed, but with an automatic system, it's not possible. But, so what happens? The fire is detected by a detection system, the system is activated, and then you see the heat release rate, forget about this first peak, it's again because of the mixture of everything, the fire is still growing. And that's also what you see inside the tunnel. When you stand there, you can see the fire is still growing, but you can walk around this fire. You can really walk around a 20, 40, 50 megawatt load without having, I would not say any problem, but if you wear firefighting clothes and a breathing apparatus, you can walk around. And if you can walk around, then any firefighter, even after 20 minutes, 30 minutes, they can come there and can extinguish the fire. Temperatures, different picture. Immediate cooling, immediate blocking of the radiant heat. To speed up a little bit. Now comes to the compensation. What does compensation mean? You want to achieve the same level of safety by other measures. Why? In most cases to reduce the costs, to be honest. You need always a proof of equal level of safety. You want to prove that you achieve the same level of safety with the new measure. You need to the equal reliability. As I said, it should be based on costs, just based on cost because you want to reduce the costs, or it's just the other measure is just impossible to realize. That's just a graph to showing the same. I have not the time now to go into the details anymore, unfortunately. So, coming a little bit about the combination, what can we compensate? Ventilation, as I said, it's extremely difficult to increase the power of the ventilation system from 30 megawatts to 100, even more. It's enormous costs, and in most existing tunnels it's just impossible to do this because they're in rural areas, they're in city areas, and it's just impossible. So it's considered that you can use a combination of water mist and the ventilation system. Why? On the one hand, the heat release rate will be limited. The truck fire I showed you, if you just would it burn without any fire suppression system, you can get easily 150 megawatt. So it was limited to 50 megawatt. That's a good thing. Of course, the smoke production rate is reduced. Even more important is the cooling effect of the water mist. Because of the cooling effect, you reduce the smoke volume dramatically. And when you reduce the smoke volume, your existing smoke extraction or ventilation system is much more effective. For sure, you can do a lot of scientific work on these effects. At the moment, we just tested them in real life, and now comes the basic work. Now we have to go back to the basic work. I just want to show you at least one short video. This is a strong backlayering. That's a pool fire of around the pools. No, that's actually a 100 megawatt fire. Now the system is activated. One thing what you see, you still have a fair visibility, and it will. Now the visibility even gets better. Of course, you have at the beginning some kind of mixture of this strong smoke layer, but normally it's not to the ground level. It's just a mixture. And now what you see is there is no smoke anymore. There is no backlayering anymore. There's no change at the heat release rate. There's no change on the smoke extraction system. This is a picture showing more even worse effect when we had a very strong backlayering. We turned on the water mist system, and the smoke really disappeared within a short period of time. What we found out that we can increase the smoke extraction or the longitudinal ventilation, the capacity or the efficiency by 70%. That's really an enormous number. So we can use a ventilation system which is designed for 30 megawatt together with a water mist system, and then you can control or keep the tunnel smoke-free smoke-free for fires of around 100 megawatts. Similar thing with the infrastructure. That's also a point of discussion. You can, because of the cooling effect, on the one hand you can limit the area of high temperatures. There are still high temperatures. Around the fire, above the fire load, you still have 700, 600 degrees. You can reduce the time of when you apply the temperature because you limit the area. And the absolute temperature is limited. Remember, Rick's water start curve or ISO curve, it doesn't matter, goes up to I think 1350 degrees. And if you just have 700 degrees, it's a complete different story for the infrastructure. Of course, you reduce the damages. Reliability, as I said already, we need to prove the equal level of safety, and this includes a similar reliability. And that's quite a new thing for firefighting systems. It's seldomly used. It's sometimes used in trains, rolling stock. It's sometimes used in cars or in planes, but in buildings. Ask a sprinkler manufacturer about the reliability or MTBF values of his system. He has no idea at all. But when it comes to tunnels, you have to do this because you changed your design completely and you replace other systems which also have a certain reliability. And then, of course, you have to do the same exercise with the life cycle costs. And I can tell you, for example, for the new time crossing, the decision was fully based on an economic base. It was just a pure economic decision because it's a public-private partnership tunnel, and the owner or the operator said, okay, even if I have just one fire in 30 years, it will save me already the money, the repair works, because I just installed a system. It's much cheaper for me. Other story, Eurotunnel, for example. They have let's say the return of investment just because of saving in their insurance after 1.5 years for the complete system. That's really dramatically, and this will change, I think, one or the other decision in the future. I just do this as a final thing. There will be some more slides then later on, as I promised, the case study of the time crossing. I skipped this now a little bit because there are a lot of pictures. You can look them later on in the presentation file. I just want to do a short advertising. There will be a conference about this solid workshop. Who is interested in fire suppression in tunnels? It will be in Berlin, Germany, of course, in June next year. And there you can also find further information on the web pages, which you then also have in the file. As I said, I will skip this now to keep a little bit the schedule. Yeah, that's all so far.